So we're going to take a look at exponential equations and how to use them to show growth or decay over time. So let's say we have a population of bacteria that's currently at 20, and let's say that population doubles in size each hour. So right now at time 0, or at the initial time, the population is 20. Okay? We could also say that after 1 hour the population would grow by 100%. So instead of being 20, it would now be double that. It would now be 40. So that would grow from 20 to 40. And after 2 hours, the population would grow again. Now it wouldn't add 20 more, it would add 100% of the last amount. So it would go from 40 to 80. So every time we go up an hour, the population size is doubling. So this can be written as an exponential equation. I can write y or f of x equals my initial value, so the initial size is 20. That goes out in front. Now, to come up with the base, I start with 100%. I need to decide, is this population growing or decaying? This population is growing. And now, by what percent is this population growing? Well, if it's doubling, then it's growing by 100% each hour. So since this population is growing by 100%, I'll add +1. And then the exponent, we can call it t, where t is the number of hours. So taking that a step further and simplifying it, it's actually y equals 20 times 2 to the t power. So notice, growth of 100% is the same thing as a base of 2. Similarly, let's say that we have a population, manatees, currently at 5,000, but this time it's decreasing by about 15% each year. So I'm going to go right to my equation. I'm going to write y equals, and my initial value is 5,000, and for my base, I start with the 100%. We're always going to begin with the 100%. Now this time, since it's decreasing, I'm going to subtract. So I'm using that subtraction sign because it's decreasing. And what percent is it decreasing by? It's decreasing by 15%. So 15% is the same thing as 0.15. Just like earlier, 100% was the same thing as 1.00. Changing a percent into a decimal is just as simple as moving the decimal place 2 places to the left. And this would be to the t power, where t is the number of years. So I could write the equation y equals 5,000 times 0.85 to the t power. Well, if we think about that for a second, multiplying by 0.85 is just finding 85% of the old amount. In other words, it's decreasing by 15% every time another year passes. So, looking at these applications, we can kind of see that if I have a function f of x equals 3 times 1.6 to the x power, the initial power, the initial value is 3. This is a growth function. And what percent is it growing by? It's growing by 60%. And how do I know it's growing by 60%? Because in order to get 1.6, I would have to have 1 plus 0.6. And there's my 60%. Likewise, if I have g of x equals 2 times 0.2 to the x power, 2 is my initial value. I know that this is decay, and it must be decay of 80%, because 1 minus 0.8 is how we get 0.2. So this is a decay of 80%.